This is Jermaine. He has 3 ways he can get home. He can go path 1 through the valley, he can go path 2 up the gradual hill, or he can go over the mountain, path 3 to get home here. Now, which of these paths will result in a greater change in elevation from his starting point to his house? I'll give you a minute to think about it. Hopefully you realize that if we're just looking at the change in elevation from where he started from to where he ended up, it doesn't matter which path he takes, because if he has to go way over the mountain, he comes back down that little bit of extra that he goes up. Or if he goes through the valley, he has to climb back up that bit extra he goes down. So the change between where he started and where he ended up is going to be the same. Now, what about the elevation gain from the starting point to his house? What is it? Again, I'll give you a minute. Maybe pause the video and treat it as a little logic puzzle. See if you can work out the elevation gain. Now, what'd you get? Let's see. Now, there are a few different ways you could solve it, but you notice I'm giving you some elevations here, so I need to work out what's the difference between the starting place and where he ended up here. And that value isn't given directly, right? That would be this value here, but I don't know what this difference actually is. So let's see what I do know. Well, I know that from where he starts to the bottom of 1, that's 6 meters. And then from 1 up to 2 is 10 meters. So if this is 6 down here and this total is 10, then this must be 4 meters between where he starts and position 2. So that's useful. Then I also know that between position 2 and 3 is 8 meters. And between his house and position 3 is 3 meters. So that means that this difference must be 5 meters. So 5 meters plus 4 meters, well, he must have to go up 11 meters to his house. And we'll put the positive in there because he has to go up. So even though we couldn't directly measure the elevation gain from where he started to where he ended up, we could figure it out if we knew some of these different intermediate paths he could have taken. Now, what if I gave you the same kind of logic puzzle, but laid out a little bit differently? So I'm giving you some positions. There's the man, here's Jermaine down here. This is a new scenario now. There's a hilltop, there is a treetop, and here's his house. Now I'm telling you that between the man and the treetop is an elevation gain of plus 15 meters. Between the hill and the treetop is plus 3. Between the house and the hill is plus 4 meters. So again, take a second, pause the video, and see if you could work out what the difference is. What's the elevation gain from the man's starting position to his house? Now we need to get to some chemistry here, and we will, but this logic puzzle is going to help us to figure it out. So we can actually treat this like a system of equations, and we can solve this algebraically. I'll show you what I mean, because what we want to figure out is the elevation gain from the man's starting position, so from the man to the house. And that's not given here directly, but I can figure it out if I can get these things to cancel. So I'll show you what I mean. Let's take my first equation. From the man to the treetop is an elevation gain of plus 15 meters. Now, I'm happy with where the man is, but this tells me how to go all the way up to the treetop. So what I need is I really need this treetop to cancel. And I can use my second equation to get treetop to cancel, but in order to get it to cancel, just like in algebra, it has to be on the other side of the equation. So these arrows here are like little equal signs. So what I need to do here is I need to flip this equation left to right. So I'm going to flip the treetop and the hill. So instead of considering from the hill to the treetop, from the treetop to the hill. Now if I do that though, not from the hill to the treetop, but vice versa, now the elevation gain isn't plus 3 meters anymore. I have to flip this sign too. because from the treetop down to the hill is minus 3 meters. So my elevation gain here is negative 3 meters. And the whole point of this was that the treetop and the treetop will cancel because it's on the right and on the left. This, if I solved here, if I added these together, this would give me the difference in elevation between the man and the hill. I'm not quite there yet because I want the difference between the man and the house. So my last equation is going to help me with that. I have the elevation gain from the house to the hill is plus 4 meters. I've got hill on the right side already. I need it to cancel because it doesn't appear in my final equation. So I need to flip this guy as well. So I want to consider the elevation gain from the hill over to the house, which will be negative 4 meters. And then once I've done this, my hill is going to cancel with my hill because it's on opposite sides. And you'll notice that if I look at just what's left here, I've got the man on the left and the house on the right. So if I add these elevations down, then that's going to give me the elevation change between the man and the house. So I have plus 15 plus negative 3 plus negative 4, which gives me a total elevation gain of positive 8 meters. And the good news is, if this makes at least a little bit of sense to you, you basically know how to do the topic that we're going to talk about in this lesson, which is Hess's Law. Hess's Law takes a similar approach, but instead of figuring out an elevation gain, we're going to figure out an enthalpy of a reaction. So why do we need this? Because it seems kind of complicated. Well, there's a problem. We can use calorimetry to investigate lots of different energy changes, but it can't be used for every single reaction. For example, rusting of iron is a chemical reaction. It's a reaction between the iron and the oxygen to produce iron oxide and iron hydroxide. But it happens so slowly that it can't be accurately measured. I have a beautiful automobile, Mazda Protégé 5. Hallelujah. It's got a friggin' Ascente goo on the badge. Hallelujah. And it's rusting, and it's rusting like crazy, but luckily it's a slow reaction. It takes many years for the car to completely rust. Hopefully a couple more years in my case. So sometimes the reaction is really slow, like in the case of oxidation of iron. Or sometimes when we do the reaction that we're trying to study, there are other side reactions that happen as well. So if I use calorimetry to try to find the enthalpy of the reaction, I won't be able to separate out the reactions that I know. And this was a problem that a chemist by the name of Germain Hess investigated. And what Hess realized is that if you treated a system of chemical equations like an algebraic system, just like you did in the logic puzzle above, and you took the sum of the enthalpies, then you could figure out the enthalpy for some reaction that you can't study directly, either because it's too slow or because there are competing side reactions. So here's a chemical equation example. We can use Hess's law to determine the standard enthalpy for the formation of carbon monoxide. So here's the reaction that I want to find the enthalpy of up here. And here are the two reactions that I'm being given. So the things that I'm allowed to do to them, just like before, is I can flip them left to right. If I do that, the sign of the enthalpy will flip as well. But I can also multiply this equation by something or divide it by something as long as I apply that change to all of the coefficients and to my enthalpy. So let's see what we need to do. I'll give you a couple tips as we go. So I'm going to look at my reaction here. I've got carbon solid plus 1/2 oxygen gives me carbon monoxide. So I see in my equation here, there's oxygen and oxygen in both of these. I've got carbon solid. It only appears in my equation once, and it's on the left side here. That's where I need it to be in the equation that I'm shooting for, right? This is my target equation. So that means I don't want to flip this one because that would put the carbon on the wrong side. And the coefficient is already what I want. I've got a coefficient of 1 here, and I want a coefficient of 1. So I'm going to leave this equation as is. So my first equation will be my solid carbon plus my oxygen gas gives me carbon dioxide gas, and the enthalpy of that reaction is negative 395.5 kilojoules. Now let's look at the second one. I see carbon dioxide and carbon dioxide. They're not even in my target equation, so they must cancel. And hey, look, here's a carbon monoxide. It only appears in here once, and it needs to end up on the right side. It needs to end up on the product side. So it's on the wrong side of the equation. That's problem 1. So I'm going to have to flip this one. And problem 2 is that here it's got a coefficient of 2. Here it needs to end up with a coefficient of 1. So I can do that. I can change this coefficient. But just like in algebra, if I make that change here, I have to make it all the way across to every entity and to my enthalpy. So I'm going to divide all of these by 2. I'm going to divide all of these by 2. So this will get divided by 2. This is a 1 divided by 2. This will get divided by 2. And my enthalpy will get divided by 2. So I'm going to make that change and flip it as I write it down. So the carbon dioxide, instead of on the product side, now it's on the reactant side, my CO2 gas, and this we divided, so it has a coefficient now of 1. My carbon monoxide is on the product side here, and its coefficient is now 1, and my oxygen, 1 divided by 2, has got a coefficient of 1/2. 1/2. And the enthalpy of this reaction, don't forget I flipped it, so it's going to have a positive sign, and I need to divide the value in 2. 566 divided by 2 gives me 283 kilojoules. Now let's make sure that everything is going to cancel like I think it's going to. So my oxygen, here I have a coefficient of 1. It's got a coefficient of 1/2 here. So I've got 1/2 on this side, a full 1 on this side. So this guy's going to cancel away completely, and he's going to take 1/2 of one of these with him, right? He won't be able to fully cancel this full mole of oxygen, but he can cancel 1/2 of it. My carbon doesn't have anybody to cancel with, and my carbon dioxide appears on the right and on the left, so they'll cancel with each other. Now let's see what we have left. My carbon solid plus 1/2 oxygen reacts to give carbon monoxide gas. And sure enough, that's what we wanted, so that's good. And then for my enthalpies, I need to add these down. So the enthalpy of this reaction will be negative 295.5 plus positive 283, which gives me an enthalpy of negative 112.5 kilojoules. Do one more example here. In an experiment to find the standard molar enthalpy of formation of butane from its elements, following reactions were determined by calorimetry. So I'm not being told what my target reaction is, in so many words, but I'm told that I have to form butane. Okay, so what's butane? Well, I've taken my organic chemistry unit, so I know that it's C4H10 butane, and it's going to be a gas. Now, if it's forming from its elements, it's forming from solid carbon and hydrogen gas. And my coefficients here, I just need to balance this equation so that I know what I'm looking for. I'm going to need 10 hydrogens here, 4 carbons here. Okay, so this is my target. This is the equation that I need to get this system of chemical reactions to cancel and equal. And this one seems really scary. Okay, I've got lots of stuff. I've got 13 halves. What the flippin' is that? I don't even know. I'm going to ignore it because it looks scary. And it actually is a good strategy. If you have a crazy fraction in one, ignore it. Focus on the things that seem easier and the fraction will work itself out. So again, my strategy is I'm going to look for the oddballs. Okay, so what are things that only appear in here once and need to end up in my equation here? One of them right off the bat that I see is butane, right? Here's butane on my product side of my target. I only see it in my system of equations once. In my first reaction, it's on the wrong side, but it's got the right coefficient. So that means that with this guy, I'm going to flip him. And then I don't need to do any other math to it. So let's flip it left to right. That'll be my first equation. 4 CO2s plus 5 water vapors gives me 1 butane and 13 halves oxygen. Now don't forget, we need to flip the sign of the enthalpy. So this is now positive 2,657.4 kilojoules. Okay, let's see what else we got here. So second equation, I see some carbon here. That might be useful because it's in my target and I don't see it anywhere else. Now it's on the right side, but it's got the wrong coefficient. I need it to have a coefficient of 4. It only has a coefficient of 1. So that means for my second one, I need to multiply by 4. So this is going to become a 4, this is going to become a 4, this is going to become a 4, and my enthalpy, I need to multiply by 4. So let's copy that down. I've got 4 carbons plus 4 oxygens gives me 4 CO2s. The enthalpy here, I need to multiply by 4, but I don't need to flip the sign. And it gives me negative 1574 kilojoules. Last one here. Okay, I see my hydrogens. That's my oddball here. I've got some hydrogens that are on the right side. They're nowhere else. I need to end up with 5. I have 2. Well, that's not going to get multiplied by a whole number, is it? If I have 5, to get 5 from 2, I need to multiply this guy by 2.5, right? Or by 2.5. 2 times 2.5 would be 5. And the hydrogen's on the right side, so I don't need to flip this one. So I need to just be careful. I have to multiply by 2.5 or by 2.5 all the way across, including my enthalpy. So let's do it here. I've got then 5 hydrogens plus 2.5 or 2.5 oxygens. It doesn't really matter whether you write it as a fraction or a decimal. And 2 water vapors. And then my enthalpy, I need to multiply by 2.5, which gives me negative 1209.0 kilojoules. Okay, so now let's go through and cancel and see if I get that target reaction that I wanted. Let's find it here. See if I get this target reaction up here. So what's going to cancel here? I've got CO2s, 4 CO2s on the left. Here are 4 CO2s on the right. So those guys will cancel with each other. I've got 5 water vapors on the left. And, oops, see, I did it again. I forgot to multiply by 2.5. Here, catch my mistake? This guy should be a 5. So my 5 waters cancel out with my 5 waters. Then my carbons don't cancel, my hydrogens don't cancel. Let's see what's going to happen with my oxygens. So I've got 4 oxygens here. I've got 2.5 oxygens here. I've got 13 halves over here. Now, we can see what's going to happen with these one of two ways. If you don't like fractions, you could just convert these all into decimals, and then you could solve that way, right? 13 halves would be 6.5. And then over here, I've got 4 plus 1.5, 4 plus 1.5, that would be 6.52. So I've got 6.5 oxygens on the left, 6.5 oxygens on the right. So they will cancel like I need them to give me this target reaction up here. Or I can compare the fractions, but I just need a common denominator, right? 4 is the same as 8 halves. And 2, well, that would be the same as 4 halves plus another 1 half. So 8, 12, 13 halves would cancel out here. So these oxygens and these oxygens do fully cancel with these oxygens here, which leaves me with 4 carbons plus 5 hydrogens reacting to give me 1 butane, which is just what I wanted. If you get something that's close, check your canceling, check that you've actually multiplied everything in here, that it's all coming out right. Then we just need to add these down, which gives me an enthalpy for this reaction of negative 125.6 kilojoules.